It is my great, all right. It is my great pleasure to introduce Professor Markus Aspelmeyer from the University of Vienna. He did his PhD in the Ludwig Maximilians Universität at Munich in Germany, working with Johann Piesl. Then he moved to be a research assistant at the same university, and then did a postdoctoral stay as a Theodor Linen postdoctoral fellow of the Alexander von Humboldt Foundation at the University of Vienna, working with Anton Zeilinger. Since 2003, he joined the University of Vienna as a faculty, and starting since 2019, he is the scientific director of the Institute for Quantum Optics and Quantum Information, the IQOQI in Vienna. He has received many awards during his trajectory. I will mention a few of them: the Science Prize of the City of Vienna, the Bertolt Leibinger Innovation Prize, the Association for Sensors and Measurements Innovation Award, the Gewin Young Entrepreneur Prize in 2014, winner in category of high tech, the Friedrich Wilhelm Bessel Research Award, the Start Prize of the Austrian Ministry of Science and Education, the Fritz Kohlrausch Prize from the Austrian Physical Society, the Ignaz Lieben Prize of the Austrian Academy of Sciences, and the Fresnel Prize of the European Physical Society, among others. He has more than 100 publications, and he has also moved into the technological side with 2 patents, which is one of the things that most of us aspire to eventually reach. The focus of his research is on quantum optical control of solid-state micro and nano objects, meaning quantum optomechanics, on the quantum foundations on microscopic and microscopic quantum physics, and finally precision tests of gravity and gravitational quantum physics. And it is really a great pleasure to have him as a host of this seminar series. Please, thank you again for accepting our invitation.
Thank you very much, Eduardo. First of all, for having me, and second, for this very kind and extensive introduction. So what I would like to do today is I would like to take you on a tour de force, if you want, starting from basic ideas how to control solid state systems, so the motion of solid state systems in a quantum regime, to using those levels of control that we achieved today to address some of the outstanding questions at the interface between quantum physics and gravity. So please bear with me for a while, and if there are questions, do not hesitate to interrupt me, or we discuss it afterwards. So when we think about the control of solid state systems with light, there's one very funny historic aspect to that. So, you know, I'm in Vienna, I'm in the 4th floor of the Physics Institute in Boltzmanngasse, and I have my office next to the old office of Schrödinger. And I have my office also very close to the library, where the letters of Schrödinger are still kept, and also copies of the letters that he sent. So I recently bumped into a letter that Schrödinger wrote to Sommerfeld in the year of 31, where he essentially complains about the fact that he calls it this fundamental question, that this fundamental question torments him, so Schrödinger, more and more. And to give an example to Sommerfeld, what they're discussing these days in their seminars is, he says, look, we have discussed in our seminar for hours and hours the following quite simple case, and then he makes this drawing. Yeah? And if you see this drawing here, this one, it says here on this drawing, it says schwerer Spiegel. This is German for heavy mirror. And then you have here, you have the dot, and it says here Lichtquant, so photon, quantum of light. And what he describes now in this letter is how the discussion went, that what happens now to the photon and the mirror, when originally, for example, the momentum of the mirror very well and the position of the photon very well. And then you just let the photon hit the mirror, and then you analyze the situation from a quantum mechanical perspective. And he describes in this letter the insight that the mirror can now act as a universal measurement tool. He says, look, momentum and position of the photon are imprinted on the mirror. Yeah, both are registered with accuracies, the product of which can be pushed way below the limit of Planck's constant. So what he has discovered back then in 1931 is what we know today as a quantitatively correct description of entanglement between light, the photon, and the mechanical motion. And this was, by the way, this was 4 years before the term entanglement was coined at all by him, by Schrödinger. And this letter also very nicely relates to something that is later being picked up again as a topic in the very famous paper by Einstein, Podolsky, and Rosen. So to make a long story short, this idea of using light to interact with a heavy solid state object and then become entangled, generate entanglement between light and mechanical motion, optomechanical entanglement, can be at least traced back to Schrödinger. What has changed over the years, so what happened in the 70 years to follow, was that one could now generate in the lab mirrors that are sufficiently small, sufficiently lightweight, such that the momentum kick of a single photon could actually make a difference. Because you can easily, in a, let's say, one-line calculation, you can ask, okay, what would the effect be if a single photon hits my heavy mirror? And then you would find out in this one-line calculation that the effect, so that the effective displacement of the mirror with respect to the mirror's, let's say, ground state wave function or the Broglie wavelength is actually very small. So eventually, the wave packet of the mirror will always factor out of the problem, and your photon is simply reflected off the mirror without ever becoming entangled in a regular experiment, unless you manage to make the impact momentum kick of the photon onto the mirror sufficiently large. And this is what essentially happened over the years, that by now we do have mechanical structures, as you can see here, micromechanical structures that are small enough, lightweight enough, such that momentum kick of let's say a low light level is already enough to displace it and then generate a sufficient optomechanical interaction. And this combination of optomechanical interactions, or the fact that radiation pressure imparts momentum on the mechanical system, that in turn then imparts back action on the light, in combination with quantum optical techniques, is something that has now become known under the name of quantum optomechanics. And the idea is a very simple one of the underlying principle. So by the way, normally if you stick with Schrödinger's original idea, again, the impact of a single photon is very small. So what you would rather like to do is, instead of just having a single photon being kicked from the mirror. So what you see here is actually now, this is indicative now for a mirror, the mass on the spring, single photon kicks, and instead of having just a single h bar k or 2 h bar k as the momentum kick of the photon onto the mirror, you build a cavity out of it. So you have a second mirror here, such that light is reflected back and forth, and a single photon can impart now a multitude of momentum kicks during the round trip inside the cavity before it leaks out again. And then you can ask, what is the effective interaction between light and mechanics? And it turns out that the displacement of the mechanical system due to radiation pressure also changes the cavity length, and therefore changes the effective energy in the cavity, which in fact then leads to enough optomechanical interaction. And this type of interaction that you can get now, so between the displacement of the mechanical system and the intra-cavity photon number, this can be used now to generate either non-classical states of light. So you can use that now for example, to squeeze light, or it can be used to act back on the mechanical system and to change the state of the mechanical system. So in a way, by producing here interaction between light and mechanics, you can then decide whether you use the light to manipulate the mechanics or use the mechanics to manipulate the light. So just to give you a very simple example, if you have this cavity with a moving end mirror, if you send light through this resonant with the cavity, you will have, of course, the light that is reflected back of the cavity will experience a phase shift that depends on the position of the mirror. And the more intensity the incoming light has, the stronger you push it, the stronger the phase shift. So that means what you generate is now a system where the light that comes out of the system has experienced an intensity-dependent phase shift. And in nonlinear optics, this is called a Kerr nonlinearity. It's a Kerr medium, and a Kerr medium can generate squeezing. So a regular Fabry-Perot cavity with a moving end mirror can serve as an optical nonlinearity. But I will show you now some examples how you can manipulate the mechanics also. And for that, let's just very briefly look at the different systems that are available. Again, the only thing you need for the effective optomechanical interaction is that the displacement of the light modifies the cavity length, modifies the cavity energy, and this quantifies then the coupling between the light and the mechanics. And the most easy thing you can have is a Fabry-Perot cavity with a moving end mirror. You can have microtoroidal resonators, for example, where you have whispering gallery modes in such toroids, where the radiation pressure is to the outside here. You can have a cavity with a dispersive element in their membrane, for example, or particles, where the motion of the particles induces via the changed index, via the index of refraction moving through here. So changing the path length inside the cavity, you can change the cavity frequency. You can have photonic crystal cavities where the motion modifies the cavity length, and you can even operate in a completely different wavelength regime, for example, in the microwave regime, where an LC circuit acts as a cavity, and you can have, for example, the capacitor part, the C part in the LC circuit, consists of a moving end, of a capacitor with a moving end plate, and therefore you generate exactly this situation. Now, let me restate what I just said and give you an intuitive picture more from an atomic physics perspective, because many of you come from that community and can immediately relate to that. There's a simple Raman scattering picture to this whole situation. So in a photon scattering picture, you can map this light mechanics interaction into a Raman scattering situation, where photons from the pump beam, so from the cavity, from the light that pumps the cavity, are inelastically scattered by the mechanical object. Right. So in a Stokes scattering process, for example, here is frequency. Here you see the envelope of the cavity, and now we have a pump that is blue detuned. In such a Stokes scattering process, you scatter photons from the pump into the cavity, where by losing some energy. The energy is, of course, lost in the inelastic scattering process to the mechanical system. In a two-mode quantum optics language, this is called a two-mode squeezing operation, where you coherently excite excitations in your cavity and in your mechanical resonator. You can also now have an anti-scattering process, anti-Stokes scattering process, where you pump your cavity red detuned, and you see you can scatter a photon into the cavity by adding some energy to the light, which means you remove energy from the mechanical system. And in this anti-Stokes scattering process, you can hence remove energy from the mechanical system, and when the photon leaves the cavity, it carries away this energy, and this is what's known as resolved sideband cooling, which was invented in the trapped ion community in the 1970s by Dave Feynman. And we can do that now for the center of mass motion of such a solid state mechanical object. By the way, of course, if the cavity does not lose the photon, but the photon is kept, what you have then is a coherent energy exchange between the optical field of the cavity and the mechanical system, which means your system undergoes Rabi oscillations between the light field and the mechanical system. But in case you want to do cooling, you simply try to make the cavity lossy such that the photon extracts the energy out of your mechanical system and you achieve laser cooling of the center of mass motion. But of course, in a nutshell, to gain quantum control of your mechanical motion, you want to minimize the coherence. So you want to have a sufficiently high optical quality and you want to have a sufficiently high mechanical quality, the latter one to prevent phonons from coming onto your system, or if you or leaving your system once you have placed them there. I give you an example for the cooling. We started effectively the attempts to laser cool mechanical motion with our cantilever structures. And you see the first cantilever structures looked like that. We essentially took a regular 1-inch mirror from Thor Labs and we microfabricated these micromechanical comb structure on it and undercut it such that at the end we only had freestanding coating structures of high reflectivity that we would now use then as an end mirror. So this would now be our mass on a spring, or our mirror on a spring, and we would just use an additional end mirror above this to generate a cavity. And you can see that here from above. This is the cavity mode on the mirror here, and then pumping the cavity, detuning the cavity, and using effectively a resonantly enhanced anti-Stokes scattering process to reduce the overall center of mass energy in our system. And our first attempts were quite humble. So we managed to go from room temperature by a factor of 30 down to like 10 to the 6 phonon of a 1 megahertz resonator. But in the course of the years, we learned how to better isolate our system from the environment. You see here the overall thermal occupation of our system was limited by the reheating rates of the system. So the cooling rate was constant, but the reheating rates of the system were too large. So we had to improve our mechanical isolation of the system from the environment, which is a mechanical engineering task. So you have to improve the mechanical quality more and more, which we succeeded to do over the years. Until then, a couple of years ago, by teaming up with Oskar Painter, we were able to demonstrate then using these laser cooling techniques and generating a laser cooled mechanical system in the quantum ground state. So basically laser cooling the center of mass motion of this mechanical system into the quantum ground state. The main trick that Oskar Painter brought to the whole community was this idea of photonic crystal cavities. And I will say something about that in the next slide. Let me just say one more thing. We thought back then, 10 years ago, hard to believe, we thought, oh, now it's going to be easy. This was an experiment we performed in a 4 Kelvin environment, so at liquid helium temperatures. And we thought, okay, now we just take this experiment and we put it into a dilution refrigerator that operates at 20 millikelvin in order to further reduce the initial temperature and then further reduce our end temperature. And this was the point where we wanted to go. And we put everything in, and you see our first data point back then was basically almost the same that we had. And it took us, I need to point that out here in red, you see, it took us another 4 years to bring the system from here to here. And we learned the hard way that there's a big difference performing an experiment at 4 Kelvin and performing an experiment at 20 millikelvin. So absorption, optical absorption at 20 millikelvin is really difficult to handle. And ever since that experience in our lab, we call an experiment that we conduct at 4 Kelvin a room temperature experiment, because the difficulties only start once you go to 20 millikelvin. Okay, so let me briefly say something about these mechanical structures that Oskar Painter pioneered. The main idea is photonic crystal cavities that are freestanding. What is the idea of a photonic crystal cavity? You have here a silicon or silicon nitride nanobeam in which you drill holes. So basically drilling holes means you periodically modulate the index of refraction, which for one direction, for example, essentially establishes a Bragg rating. So when light wants to travel in this direction and it sees this periodic modulation, you get perfect reflection back. You do that also on the other side, and you let a defect in the middle, such that when you launch an electromagnetic wave here in the middle, for example, through a tapered fiber, light is confined because it cannot cohere. This is like a Fabry-Perot cavity, not just in a nano structure, where light is really confined now in the smallest possible mode volume of 1 over lambda cubed, and you get very high optical quality in this structure. Now, if it's freestanding, you also have mechanical motion that you can co-locate with the electromagnetic field. And the whole idea of optomechanical interaction is, as I said, that motion couples to the cavity energy. And this, of course, in the co-localization is optimally achieved. And what you have now is a system with high mechanical frequency and extremely high optomechanical interaction. So high frequency, 5 gigahertz, means that if I take a 5 gigahertz beam and I place it in a 25 millikelvin environment, which we can basically already cool all the thermal occupations of the system out. So just by placing this photonic crystal cavity into a dilution refrigerator already means that you have a system in the quantum ground state to start off with. And now you can really do quantum physics, okay? Because remember, when you have your system in the ground state, you could now then again do Raman scattering process, you do a Stokes scattering process to create a single phonon in your mechanical system by scattering of a Stokes photon. Okay, and you can also read it out, for example, by now having an anti-Stokes scattering process. So you will by pumping this cavity, you will scatter an anti-Stokes photon by only then when there's a phonon into your system. Eduardo, there was a question.
Yes, I just wanted to make a question that it's a common confusion. If you go one step back, when you use the laser cooling, you can then cool the device on the basic center of mass mode to the ground state, but still the device can be at room temperature. So how come is it possible to have atoms that are at room temperature and still have the center of mass motion to be in a quantum state?
So it's basically so everything is in these experiments, it's pre-cooled. So these are experiments that were performed at 4 Kelvin and 20 millikelvin, but still, of course, the ground state temperature is in the microkelvin regime, right? So you need to distinguish the internal temperature of the system, which is essentially the temperature of the electrons, and the variance of the center of mass motion. Okay, so this is the difference. So the overall center of mass motion of the atoms can be confined to the quantum ground state, but the internal temperature, the electron temperature, can be still very high. So I agree that this one needs to be careful of this distinction. Yes.
Thank you.
So it means there's a lot of black body radiation that is emitted from this object. Okay, so it localizes very quickly. I come back to that later when we will at some point ask how large can we make a quantum system actually. So basically the wave packet. Then this is exactly the limiting factor Eduardo that you just mentioned. The fact that we still have a very hot surface that radiates a lot of photons. Very quickly, just to give you a feeling how such experiments typically work, you have here in your cryostat, you have your photonic crystal cavity, you have a fiber taper. This is also in that case a silicon nitride waveguide where light is guided. You evanescently couple light into the cavity and couple out again. And now imagine this is already in the quantum ground state. So again, quantum ground state meaning that the center of mass motion is described as a quantum harmonic oscillator sitting in the ground state. Then you can pump now your system, for example, with a blue detuned with a pulse that is blue detuned with respect to the cavity. It hits the cavity. It can generate in a Stokes scattering process. It can create a Stokes photon which is resonant with the cavity. So it will be taken out again and can be detected in a single photon detector. And you leave the phonon behind, a single phonon excitation. If you want to read it out, you send a red pulse. If there's a phonon there, there's going to be an anti-Stokes scattering process, and you can again detect the anti-Stokes scattered photon in the single photon detector. This is also a way, of course, to measure the temperature, because if your system is in the ground state, you cannot extract any more energy. So if you now send a red detuned laser that would extract via an anti-Stokes scattering process energy out of the system, it cannot happen when the system is in the ground state. So that means the more you are in the ground state, the less anti-Stokes scattering processes should be able to occur, because you cannot extract any more energy. You can always deposit energy, so a Stokes scattering process will always be possible. So the closer you are to the ground state, the stronger will be the imbalance between the anti-Stokes and the Stokes scattering processes. And this sideband asymmetry is something that is well known from the atomic physics community, the laser cooling community, and you can use that now to do thermometry of your state. And this is what we did here in our experiment first. So we measured for the system that is thermalized to the bath temperature of the cryostat, we measured the Stokes and anti-Stokes scattered photon rates, and from the imbalance we can compute the average phonon excitation in the system. And remember the theoretical value that we expected is 10 to the minus 5. We observed 10 to the minus 2. That's still a very low occupation, but there's a 3 order of magnitude difference between theory and experiment. Okay, and it's definitely not the cryostat temperature. The difference is really the heating inside the structure. When phonons are being absorbed in a 25 millikelvin environment, they heat the structure up very strongly, and it's very difficult to get the heat out again. This is why people, for example, today are also going into different materials. You find a lot of diamond-based photonic crystal cavities and so on. So very quickly, because I would like to conclude this first chapter here, and now you can do something that has not been possible before. You can do single phonon quantum optics. So you can do quantum optics experiments instead of photons. Here now you have single phonons. So for example, you can essentially redo a beautiful experiment from Henry, Brown, and Twist. You can do 2 photon interferometry, or in that case, 2 phonon interferometry. It's called intensity interferometry. I apologize. With single phonons by generating a single phonon excitation. So this is the Stokes scattering process that generates now a phonon, and by sending that on a beam splitter and showing that there is no coincidences, which basically gives you a G2 factor. So below 1, which is indicative of a non-classical state of, or let's say a non-Gaussian state of motion of your mechanical system. What you can also do is, instead of taking 1 photonic crystal, you can take 2 photonic crystals, and you can do the following. You can now have your blue pump again that generates a phonon inside your structure, remember? You can send it on a beam splitter, and you can now either excite your photonic crystal A or your photonic crystal B that can be far away. So in our case, it was separated by a few centimeters inside a fridge. Okay? So you can either excite a phonon here or a phonon there. That's single phonon excitations. And of course, you would know which of the 2 were excited, because where you create the phonon, there would also be the Stokes scattered photon coming out. Okay, but then what you do is now you erase this information by sending the output modes of your cavity on a beam splitter, such that behind the beam splitter, you cannot tell anymore, if you detect a photon here, whether the photon was coming from this photonic crystal or from this solid state object. And that means you have now generated an excitation on one of those 2, but you cannot know in principle where it is. And this is called entanglement. So what you have done now is you have generated an entangled state between those 2 distant photonic crystals, in other words, you have delocalized a single phonon over different devices. This is the so-called DLC-set protocol after Duan, Lukin, Sirac, and Soller, who implemented that as a primer for long-distance quantum communication. And in fact, this is the beauty of those mechanical systems, these optomechanical systems, that you can engineer them. And you can tailor them to arbitrary wavelengths, in particular to telecom wavelengths, and you can then use the mechanical degree of freedom as a transducer, as a storage element. You can store optical information in there. You can transduce other degrees of freedom, electrical degrees of freedom, and so on to the optical domain and back. And this has become now quite a powerful technique. Okay, so I wrap up this first part here, where I basically wanted to give you a little bit of an introduction and of an overview of what is being done these days in the field of quantum optomechanics. So today we are now in a situation where many labs around the world now are able to control mechanical systems in the quantum machine. So we have, for example, quantum ground state of motion, as I showed you, via laser cooling or just via brute force cooling. We can now also generate squeezed state of motion of the mechanical system. People have also borrowed again in ideas from trapped ion physics, reservoir engineering that was invented by Sirac and Soller many years ago. People were able to create non-Gaussian quantum states of motion. I showed you one example here where we were able to use scattering of light to generate single phonons, so Fock states on a mechanical resonator. And there are many papers by now that demonstrated quantum entanglement either between light and mechanics or between two mechanical oscillators, and either in the domain of continuous variables or in the domain of discrete degrees of freedom. This has now developed into many different directions. Eduardo has already mentioned commercialization. So there have been some attempts, and not only from my team, from several other teams also. And you can see, for example, in the domain of precision interferometry, the mechanics of optical coatings has resulted in quite some new insights, and the design and invention of new optical coatings that have also quite an impact on, can have quite an impact on gravitational wave research. In addition, these ideas of optomechanical interactions are being used now very intensively to improve the sensitivity of gravitational wave detectors. So for example, this recent Nature paper here of the LIGO community, what they did was they used squeezed light input in combination with what I told you just before, this optomechanical Kerr effect. So this the generation of squeezing through pushing the mirror by radiation pressure, and the combination of those two, a squeezed input and ponderomotive squeezing inside the LIGO cavities, results then in sensitivities below the so-called standard quantum limit in detection. You see the transduction route is being heavily played. There are now ideas and actually experiments where the mechanical element is used to transduce excitations in the microwave domain into the optical domain and vice versa. So this is something that is quite relevant now in the days of quantum information processing, where you have stationary qubits in the microwave regime with superconducting circuits, and you somehow want to get out and connect them to other machines, which is best done via optics. So you need an efficient transduction on a single quantum level. And you see here that mechanical elements are very promising. There are other ideas of quantum transduction and sensing. I don't go into the details here, on-chip signal processing, and further mechanical sensors for current searches for new physics, such as dark matter and so on. But basically, each of these topics is a separate talk, and I just wanted to give you sort of an overview. So I think this is a good time for a quick break. And I see I'm already very late. I apologize for that, because I still have the second part that I would like to hopefully not bore you with, but would like to motivate you with. So if there are some questions, now would be a good time.
So if anybody has any questions, you can raise your hand and we can habilitate the phone. So while they raise their hands, let me ask, many of these things are like following the book of quantum optics, using photons now traduced to phonons. What
Yes.
would be the advantage of having phonons as opposed to using photons? Do they interact more? What kind of advantages they offer?
Okay, I give you just one example. Okay, so one example is something that is now practically being used, or is tried to being used in a quantum information processing community. One question is, how can you have superconducting circuits interact with each other? Okay, and normally, if you look at the literature, what people typically do is to do that via photons, microwave photons. Okay, and it turns out one advantage of phonons is phonons have a much longer wavelength, which leads to much smaller losses. So you can achieve coupling of arrays via phonons with much smaller losses. So this is a very practical advantage. And at the same time, you can also increase the coupling. So this is just one example. Yeah, in particular lossless.
Jorge Hirsch asked, do you have limits for collapse theories as the numerical of atoms is so large?
As the what of atoms?
Numerical, the number of atoms is so large. Do you have limits?
Yeah, exactly. Yes. So I come to that. Yes, thanks a lot. Definitely. So these many of these collapse models introduce some stochastic heating. So it turns out that many of these collapse models, for example, would result in anomalous heating processes that you could experimentally measure or rule out. Okay, and just doing thermometry on massive mechanical oscillators already allows to rule out new parameter regimes in these collapse models. Yes. So there are a couple of works that have been done. If you're interested, I don't know where the question came from. If you drop me an email, I can send some references here. Fantastic.
I think there are no more questions right now. Probably we can continue then.
Okay, very good. Now comes the interesting part. So because now I tell you what I find interesting these days. So this whole I was always fascinated by this idea being able to manipulate like solid state systems in a quantum regime. I really started all of that out of sheer curiosity and a really intellectual curiosity, because I just was very fascinated by the possibility of doing that. So I had previously learned about entangled photons. I had a background in solid state physics, and this combination was very fascinating. Now, while I was studying all these things, and this comes now to Jorge's question a little bit, I basically realized that there's one thing that is really special about using these mechanical systems, and it's not the phonons per se, okay? But what is special is the number of atoms. You have so many atoms in such a small volume. Yeah? So you have solid state densities, and this is different to dealing with single atoms. This is different to dealing with atomic gases and so on. So suddenly you can cramp many atoms in a small volume of space. So there's a very natural question that popped up. Could it be possible that these experiments can lead to a new class of quantum experiments where we can have a gravitational source mass, so that the mass that produces the gravitational field in the quantum machine? This is the question. So is all of that what I was saying now, what we have been developing the last 15 years essentially, could this be a way towards preparing a massive system in the quantum regime where the mass is so large that it produces a gravitational field that can be measured? And could that then mean that there could be a road towards measuring gravitational fields that are generated by quantum states of masses. Yeah, that's the question. In order to answer that, let me just give you a little bit of a background. So background number one is again an historical one. If we talk about gravity, then of course in the history of gravity, mechanical systems were always helpful. Okay? So it was actually it were mechanical systems that helped to measure gravitational fields on the planet. So this was already in the 18th century. This was a big step to go from the idea of having gravity not only being carried by celestial objects, but also being carried by objects on a celestial body like the Earth. And so people basically started to measure gravity from things other than planets. There's a beautiful experiment by a guy called Maskelyne in the mid 18th century, who measured the gravitational field, attempted to measure the gravitational field of a mountain by having a pendulum and measuring the displacement, so that the deflection of the pendulum through the gravitational interaction with the mountain. And it was the displacement measured with respect to the fixed star horizon that they did. The error bar was very large in this experiment, and it was one of the things that motivated Cavendish to do his very famous experiments to measure gravitational forces of small spheres, well, small compared to planets, with a torsional pendulum. And nowadays, if you look in the best experiments, so now we have tabletop high precision experiments of gravity, and that allow one to measure, for example, the gravitational force and Newton's constant down to the precision of a relative precision of 10 to the minus 5 in these famous experiments by the Edelberger group in Washington. So this is currently the state of the art in precision measurements of gravity on Earth. So what about the quantum side? We also know very well already, both in theory and experiment, how quantum systems react to gravity. So when we have a quantum system and we immerse the quantum system into a gravitational field, what does the quantum system do? We have beautiful, really incredible experiments that show the influence of Earth's gravitational field on the wave packet of quantum systems. One of the most early one in that respect, is the seminal paper by Colella, Overhauser, and Werner, also called the Cow experiment after the initials of the authors, who showed how a neutron wave packet that traverses through the classical gravitational field of the Earth picks up a dynamic phase. And what the way how they see it is, of course, they measure a phase difference because they have a neutron interferometer where the neutron is going two possible paths, each at a different gravitational potential, meaning picking up a different phase. And if you rotate now this interferometer in Earth's gravitational field, you change the phase difference of the dynamical phases in the two paths, and you see interference fringes that are generated really by the impact of Earth's gravitational field on the neutron wave packet. And this, of course, has become the basis of the many absolutely fantastic experiments in atom interferometry to measure the gravitational field of the Earth using atomic fountains, like the beautiful experiments that Eduardo is also doing. Now, another example is an experiment by the Vineland group. I'm zooming in here quickly on the gravitational redshift. So what also has been shown is that Earth's gravitational field can have an effect on the frequency of optical clocks, for example. So here's an experiment by the Vineland group. They have an optical clock here on their table, and they could show how the frequency of the optical clock changed when they lifted the table by 30 centimeters in the gravitational field of the Earth through gravitational time dilation. Now, all of these experiments, again, they're really beautiful, and essentially they're right now the best methods to really probe gravity. There was just a couple of weeks ago an incredible paper by Junyi's group in Boulder at NIST, where they showed more or less an experiment of that type, but not on a 33 centimeter level, but on a millimeter level. So they were sensitive to Earth's gravitational field on the millimeter scale of their atomic ensembles. And all of these really fantastic experiments, they can be understood within standard quantum theory. Okay? So in the worst case, so to speak, it's a quantum field theory that is lives in curved spacetime. Okay, and with that you can describe everything. The question that I would like to ask now is, instead of having quantum systems as test masses in an external gravitational field, can we think of quantum systems as source masses of the gravitational field? Or in other words, instead of asking how do quantum systems react to gravity, we ask the question, how does gravity react to quantum systems? And again, I would like to make a brief historical account. If you look back in the literature, there is the famous Chapel Hill conference where Feynman proposed a Gedanken experiment that is essentially to the point what I was just asking. He says, okay, in order to answer this question, how gravity reacts to quantum systems, one should think about designing an experiment which uses a gravitational link and at the same time shows quantum interference. Okay? And what is the idea? The idea is you take a mass, the mass carries a spin, and you send it through some sort of Stern-Gerlach device in such a way that you then have a coherent superposition of the mass being here or being there. Yeah? So you generate a superposition of macroscopically distinct states, center of mass states of your mass. Yeah? And then you take a second mass. So here's your mass 1, here's your mass 2, and you let the two couple via gravity. Okay, what's going to happen? Well, from a quantum physics point of view, the situation is extremely simple. If you have here a superposition of the two center of mass states, then you will also have a superposition of the gravitational fields, which means that both branches interact gravitationally. And you will, through this interaction in both of these branches, generate over time an entangled state in the position of these two objects, of these two masses, where the entanglement has been generated via gravitational interaction. Easy. Yeah? From a quantum physics perspective, this is a very natural consequence. The interesting part is actually from the gravitational perspective, because from a general relativity point of view, right? This is the underlying theoretical framework of general relativity, Einstein's field equations. And the generation of entanglement is fundamentally inconsistent with having a fixed space-time metric that is generated by a source mass configuration. So in other words, having a superposition of a source mass is a concept that is ill-defined in a general relativistic framework. Or again, in other words, in a general relativistic framework, gravity is you can map the gravitational force essentially to a situation where a test mass is following a geodesic, so it's basically following geodesic motion in a curved space-time where the curved space-time metric is provided by the source mass. Okay, now no matter what the source mass distribution, if the source mass generates a fixed space-time metric and your test mass is separable from your source mass, then there will never, through geodesic motion, be entanglement generated between those two, because it just follows along a geodesic. So the only way you can, by geodesic motion, generate entanglement through geodesic motion is actually if the space-time metric itself is in a superposition, and that then generates the entanglement. So in that way, the question that you actually ask with such a type of experiment is, does gravity require a quantum description? So if you generate entanglement via such an experiment, if you generate entanglement via gravity, then this cannot be explained by a purely classical GR framework. So that means that you need at least have to have something like a space-time inner superposition. So it means the superposition principle has to be applied also to the metric. And this is what you could call actually a quantum nature of gravity. Just one more word, it does not tell you anything about the field degrees of freedom. Okay, I mean, we are in a luxurious situation as quantum optics people, because with photons, we always have the field degrees of freedom. What I'm saying here has nothing to do with the field degrees of freedom. So there are no gravitons evolved whatsoever. It's really the very first step, asking the question, do we require a quantum description at all? Do we at all need the superposition print? Can we apply at least the superposition principle to the gravitational field? And just to make sure, no experiment to date exists that would answer that question. So we do not have a single experiment that would tell us whether gravity requires a quantum description. We have a mathematical framework for writing down a quantum theory of gravity, but we don't have experimental evidence that this would actually be required for nature. Okay, so this is the whole point. Now I need to speed up a little bit. I tell you now our two approaches that we are currently following. Okay, so our question that we're asking is more or less a reality check. Okay, so can we really have quantum systems as gravitational source masses, or is this just some lucid dream? Okay, and in order to answer that question, we need to answer two other questions, namely, how small can we actually make a source mass and still measure its gravitational field? So how can we how well can we isolate gravity as a coupling force? Okay, because if all electromagnetic interactions dominate, then there's no point in trying to do the experiment. Okay, so we need to be able to isolate gravity as a coupling force. This is the first one. And then the second one is, of course, how massive can we actually make a quantum system? So is it really possible to think about having a superposition of macroscopically distinct states of a solid state massive object, which is so massive that we can have a gravitational field that we can actually measure? These are the two questions. And in my remaining few minutes, I would very briefly just show you where we are with that. Where do we stand right now? You see, from a quantum physics perspective, there are a lot of experiments, and these are now only the experiments where I look at the spatial degree of freedom of a quantum system with large delocalization or with some delocalization. And there are experiments like the wonderful meta-wave interference experiments of my colleague Markus Aspelmeyer in Vienna, where you have very long coherence times, but very small mass. Okay, so you really need to go to the solid state. These are type of the experiments that I already showed you, but there the coherence time goes down. Okay, so basically we have this regime right now. And on the gravity side, what we have is the smallest source mass, gravitational source mass that people have measured the gravitational field of these days is a gram. Okay, and so now our task is to shift this block here to the left, to isolate gravity of smaller and smaller masses, and to shift this block here to the right. Okay, and this is what we are trying to do. So one type of experiments that we are performing at the moment is experiments where we try to measure the gravitational field of the smallest gravitational source masses. And what we have here is at the moment a small gold mass of 1 millimeter in size, of which we measure the gravitational field. And the idea is very simple. You take the mass here and you basically periodically drive it here in time. And by doing so, you generate a time varying gravitational field at the location of the test mass. Which also means you have an acceleration that depends on time due to gravity. You can compute all that. And you see that for the masses that we have on the order of 90 milligram and modulations on the order of a few millimeter of the source mass, we get accelerations on the order of 10 to the minus 10 meter per second squared. So 10 to the minus 11 G. So in other words, we modulate the source mass here and the test mass only moves by a few nanometers. Okay, which already shows you where the challenges are. The challenges are to distinguish gravitational acceleration from seismic acceleration. As a noise is really a big issue, and I don't go into the details here of this plot, but let me just tell you that our biggest sources of distraction are the traffic light of a road crossing a few hundred meters away from our lab, where the traffic light cycle coincides with the resonance frequency of our experiment. Okay, so exactly at 10 millihertz, we see a very strong signal due to trams accelerating, buses, cars accelerating, pedestrians, and so on. And we also even see the difference between Friday and Saturday night, where people are out to party, and the regular nights where people are not on the street. We can distinguish that because during the night there is no trams, so we get these very dark spots with low noise. But you see some of these dark spots are brightened again due to people on the street. Well, so these were things that we had to fight. Also, even the gravitational field of a tram that was passing close to our lab. And eventually we managed to measure gravitational signal of a 90 milligram source mass, and with a precision down to like 1%. So it means an acceleration sensitivity of 10 to the minus 12 meter per second squared. What is next here? Next is we, instead of having a 1 millimeter sphere, we want to go smaller. And we are even thinking of measuring the gravitational field generated by a mass that is as small as the Planck mass, so 25 micrograms, sorry. And in order to do that, you really need to improve on seismic isolation. And the way we are doing that is we are moving our experiment currently into an underground mine, where we are perfectly shielded from the environment. And we already did some preliminary measurements just on the vibration levels, and they are extremely encouraging. Okay, so I really need to wrap up. Let me very briefly highlight the quantum part also. So the quantum part basically rests on the ideas that I have already shown to you, but in a way we want to combine the best of two possible worlds. So I showed you how we can achieve quantum control over solid state devices. You know very well these wonderful matter wave interferometry experiments, where you have essentially free falling atoms, molecules, and so on. And what the two are in a way complementary. So in the matter wave interference experiments, they have extremely long coherence times that we would like to have. In experiments with solid state systems, where we have the very large density and large number of atoms that we need for the gravity experiment. So somehow we need to combine those two. And the idea that's developed was essentially you combine them by combining the best of two possible worlds. This one is free fall, and this one is solid. So what we do is now we have solids in free fall, or essentially not really free fall, but we trap them in traps such that they can levitate, and we can totally freely change the dynamics of this trap and can change the potential landscape and have so free access to the dynamics of such a levitated particle in an engineerable potential landscape. The things that you can do is, this you are well aware of, you can obviously trap such microparticles. So in this case, this is a 200 nanometer, 150 nanometer silica particle in an optical tweezer. If you remember from your dipole interaction between light and the polarizable object, it's actually the beam intensity that provides you with the overall potential landscape that the particle sees. So a Gaussian beam produces an inverted Gaussian potential. That means that for small displacements, you get harmonic motion, harmonic confinement in all three directions. So this is why a focused laser beam provides you with a 3D optical trap for the motion of such objects. Once you have that, so once you're trapped, and you can see here a bead trapped in front of a microscope objective, what we do now is we have not only read out in the forward direction, so the light that is scattered in forward direction, we can read out the X, we can extract the X, Y, and Z motion, which we use to stabilize the particle motion in a feedback circuit. But what we can also do is, and there we can stabilize the particle at the very low pressures. What we can also do is we can take the light that is reflected back, we can read that out in a way that is close to Heisenberg limit. That means that we can acquire the particle precision with a the particle position with a precision that is close to the quantum ground state. So again, this is a room temperature particle that is moving in an harmonic trap, and we can monitor now its phase-space trajectory with a precision that is close to the quantum ground state. Which also means now we have the quantum trajectory of the particle available, and we can use this information now to just stabilize the position in a simple feedback loop. Okay, and stabilizing the position when you have ground state limited precision in the readout means that you stabilize, you cool your system to the quantum ground state. So we can now prepare the quantum ground state of motion of a 150 nanometer levitated particle in ultra high vacuum just by readout and feedback. And this is a picture, by the way. So here, this is a picture of our 150 nanometer glass sphere, or scattering of the glass sphere that is kept at room temperature and is, while this picture is being taken, cools to its quantum ground state or in its quantum ground state of motion. For reasons of time, I skipped the other methods that we have developed, which basically is one that was invented by Helmut Ritsch in Innsbruck and by Vuletic and Chu independently back then in Stanford, which is called coherent scattering, and it was invented back then as an add-on to laser cooling for molecules. So the question was, how can you cool the motion of a particle, the motion of an atom, if you don't have access to the regular energy levels? And the idea was, well, have it in a cavity, and same thing that we already discussed. Okay, the photons that are scattered off the particle can be resonantly enhanced by the cavity. And if you detune the cavity such that you resonantly enhance only the anti-Stokes scattered photons, so the ones that take out energy from the system, you effectively laser cool your particle, and you can do that into its quantum ground state of motion. And this is something that we have done in an experiment. We teamed up here with Vladan Vuletic at MIT, and then managed, this was mainly Uroš Delić's work, managed to trap the particle and then make the cavity resonant to the anti-Stokes scattered photons from the microscope objective, so those that carry away the energy, and then see it basically cool down to its quantum ground state of motion. Okay, so I wrap up here. It's I guess it's already been quite long. I just mentioned very briefly now the next challenges that we have. The next challenges is we have now prepared our particle in the quantum ground state of a trap. The trap is an harmonic trap and with a few kilohertz, so that means the wave packet size is on the order of a few picometer. So we have prepared now a few picometer wave packet of 150 nanometer particle. But what we are really interested in is now to generate a large wave packet. We want to have a large delocalization of our wave packet. The question is now how to do that. One possible answer is free fall. You just switch off the trap. Just the dispersion of the wave packet will result after a few milliseconds of fall time in a wave packet size that will be larger than the particle. This is one possibility. There are other possibilities to do that. There are a couple of ideas out there. Again, I won't go into the details. The ideas like free fall and measurement to produce then superpositions of macroscopically distinct states of the center of mass. Vollmann has had some beautiful preliminary experiments where you do a full Stern-Gerlach type experiment like the one that was suggested by Feynman. And you can do all of that possibly to generate then at the end of the day these macroscopic states. I think I stop with that, and I show you here my summary. This is the overall summary. What I have showed you is that we are now looking into the quantum optical control of levitated systems in a regime of large mass and long coherence time. There's a bottom-up approach where coming from quantum systems with like 10 to the 9 atoms, quantum states of motion with 10 to the 9 atoms, we want to go up and increase the mass even further. And from a gravitational point of view, as a top-down approach, we want to isolate gravity's coupling force from smaller and smaller objects, and eventually hope to bring these two domains together. So with that, I simply stop. I leave this slide here, the summary slide. I say a big thank you to my team, and leave the floor now for discussion.
Thank you very much for the fantastic lecture. This is really a very intriguing question, the one that you're posing. So if anybody has any questions, you can raise your hand, and soon Gina will open the microphone.
Jorge Hirsch he sent in the chat that it was amazing. Congratulations. Yes.
Thanks a lot, Jorge. Thank you.
So while they start with the questions, let me start with one myself. So I understand that now you want to have an extended gravitational source mass, let's say a superposition of mass in two places.
In the long future, okay? This is long term.
Okay.
Yeah,
so
that would be the ultimate goal. Yes.
I understand that it's important that the masses are big so that the gravitational source is big, but I would imagine that it's also useful that their separation is big as well. So my question is there a figure of what is the figure of merit that tells you the ideal one? What's the combination between mass, size, and so on?
Thanks. Yes, thank you very much. So for reasons of time, I did not show that. But there are actually, if you look in the literature, there are already a lot of papers, I have put them here, that address exactly the question. So if you really now want to put some numbers, so to speak, to Feynman's proposal, how do you do that? Okay, and so let's say the overall question is, what does it take to generate entanglement via gravitational coupling between two objects? Okay, and there are two possible strategies to do that. The first strategy you see here on the left. The first strategy is mass 1 is just a harmonic oscillator. Mass B is just an harmonic oscillator. Okay, but they're quantum harmonic oscillators. Okay, and they just couple now via gravitational interaction. This coupling will result in entanglement between the two. Okay, and then you can compute the entanglement rate between for the gravitational interaction. Okay. Before I tell you the outcome, I tell you the second possibility. The second possibility, this is one that has recently been suggested by Zogato Bozo and others, and Maletta and Vedral, is that instead of taking two harmonic oscillators, you take two superpositions. So each of the masses is in a macroscopic superposition. Okay, so mass 1 is in a superposition, mass 2 is in a superposition, and you let those couple gravitationally. And also there, the gravitational coupling will now generate entanglement. So these are the two possibilities. And it turns out the rate at which entanglement is generated is the very same for both approaches. Okay, and now here's the figure of merit. You see the rate scales with, well, it's Newton's constant divided by h bar. Well, okay. But now you see what matters is actually the mass squared and the delocalization squared. So what is this delocalization? This delocalization is, in this case here, in the right case, is the size of the superposition. And in the other case, in the harmonic oscillator case, it's the size of the wave packet. Okay, so either you make a large wave packet or you make a large superposition. Okay, basically it's up to you. So whatever you find, let's say, more simple. I personally, I cannot give you an answer yet. Okay, I'm still undecided. There are ideas how you can do this. There are ideas how you can do that. Both are super difficult. So I guess time will tell. It's now the coherence that matters. But the short answer to your question, what is the figure of merit? Well, it is actually mass squared times delocalization squared times coherence time. Okay, so it's the product of these three that needs to be large in order to make this experiment successful.
Do you know the typical values for this rate?
So I can again here. I skipped a couple of slides. So here are typical values. Okay, so if you go to the Macromolecule Experiment by Markus Aspelmeyer's group, where they have you see a particle with 10 to the minus 23 kilograms, but delocalized over a large size. Okay, 500 nanometers. So the delocalization is much larger than the size of the object. You get a delta x times m on the order of 10 to the minus 29. Okay, whatever, it's a number. If you take the solid state mechanical oscillators these days, you see it has 10 to the 13 atoms, right? Instead of 10 to the 3. So you have 10 orders of magnitude more atoms, but the superposition size is 9 orders of magnitude smaller, or 10 orders of magnitude smaller. Right? So that means delta x times m is 10 to the minus 29. So it's very funny. In these two experiments, this product is the same. Okay. Nice. Still, the macromolecules win right now because the coherence time here is a second, and here it's a nanosecond. Okay. So it's this you need to multiply with the square root of the coherence time. Then you have like 4 orders of magnitude where this one is better. But still, for these masses, they are way too small to produce anything useful.
I see. Okay. Are there any other questions? Please raise your hand.
They are very shy.
It was a lot of information.
So nobody? No. What happened? No.
So then I will take
you keep going.
I understand the point of the difference between changing the source and changing the test mass. But one would imagine that there is some reciprocity relation between these two guys, right? It sounds like strange that one is not equivalent to the other. Do you have any questions on this reciprocity?
Yeah. Okay, good point. So I mean, I've cheated a little bit. Okay. So this distinction of source mass and test mass is a very idealized situation. So in gravity textbooks, when you talk about a source mass, this is typically this is the mass that generates the gravitational field, so that bends space-time, if you want. And the test mass is a hypothetical object that has no back action on the source and has no effect whatsoever on the metric. So basically, test mass just feels the metric and follows a geodesic along the metric. And this situation is totally non-exchangeable. Okay, the one creates a gravitational field, and the other one just feels it. So this is by definition a non-reciprocal situation. Okay. In reality, of course, you're fully correct. In reality, you have two masses, and the one will have also a back action on the other. Okay, and the way how in our case we sort of stop this reciprocity is that it's the one mass that we really change, which means that this mass here, the other mass that we call the test mass, really sees a changing mass distribution in its vicinity. And so it's really for this mass that sees a change in the space-time structure, right? And we only look now at the acceleration of that mass. Yeah. Okay. And in principle, you're right. If you go in the reference frame of this mass, yeah, then this mass will see this mass coming back and forth. Right, and so this should also have an acceleration, but we are not measuring. Okay.
Okay. All right. So in case somebody measures the coherence due to the wave packet expansion, that would not be enough test of what you want to see.
Well, you know, but just by expansion, no. But if it's loss of purity due to coupling, due to gravitational coupling, that's different. No, this could be a signature of entanglement. I mean, it's not a bullet. It's not a bulletproof. It's not bulletproof. So it's not a smoking gun, but it's an indication. Okay. Yeah. So imagine you have your two harmonic oscillators, and you know the purity in which you prepare them. Right? And then you switch on the coupling, whatever that means, right? And you lose purity. Yeah, that's entanglement would do that. I mean, other things could also do it, right? But it would be better than nothing. I would say it's an indication. Yeah.
All right. Any other questions? This is your chance to do them.
So while you are still thinking, I just introduce you to my team. So this is a very old photo. I apologize. It's very old because you can see by now the team has really grown a lot. Wow. And we have now different teams working on all the different aspects of what I just told you. And we have really fantastic people both on the postdoc and PhD level, also a few master students who have joined us, and really extremely creative, and we all have a lot of fun.
Great. All right. So if there are no more questions, we thank again Markus for this fantastic talk. It was great to hear about these topics, and we hope that next time we can have you in the presential manner.
Definitely. I mean, it's a much better way of discussing. Yeah. It's if one is here in person. I'm pretty sure over beers we would have many more discussions.
Yes, we are crossing the fingers for being in Mazatlan.
Yeah. Exactly.
Yes,
keep me in the loop. Yeah.
Right. For sure, believe me. Thank you so much, Markus, for accepting our invitation.
No, thanks, Gina. Thanks, Eduardo. It was really a great pleasure. Thanks a lot. And all the best. And please don't hesitate. Yeah, thanks. Please don't hesitate to reach out in case there's some follow-up questions and so on. I'm more than happy to respond also via email.
Yeah, I may do that because I still have some other 5 questions.
Yeah, you already have like 5 from Eduardo in your email in the inbox.
Okay.
Yes. Now, if anybody wants to, as Professor Aspelmeyer is saying, if you want to get in contact with him, you can send me an email. And I can share the contact with you. Thank you so much, Markus, for accepting our invitation. And thank you so much, everybody out there. Thank you, Eduardo, for being the moderator in this session. And see you later, guys, next week. And thanks so much, everybody. Go and have lunch. Good night, Markus, for you.
Thanks. Yes,
and
I will.
See you later, guys. Bye.
Bye. Bye.